Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum. Guglielmo Marconi's first radio transmissions in 1894 have spread into space for over 100 years at the speed of light. They passed Sirius in 1903, Vega in 1919, and Regulus in 1971. That signal has already passed over 1,000 stars. Anyone orbiting one of those stars with a really good receiver could detect Marconi's signal and know that we are here. Radio waves are the longest and contain the least energy of any electromagnetic wave. While visible light is measured in minute fractions of an inch, radio waves vary from about 19 centimeters, about the length of a water bottle, to waves the length of cars, ships, mountains, all the way up to monstrous waves longer than the diameter of our planet. Heinrich Hertz discovered radio waves in 1888. The first commercial radio station went on the air in Pittsburgh, Pennsylvania on November 2, 1920. Then, in 1932, a major discovery by Carl Jansky at Bell Labs revealed the stars and other objects in space radiated radio waves. Radio astronomy was born. However, scientists need giant antennas to detect weak, long-wavelength radio waves from space. The enormous Arecibo radio dish antenna measures 305 meters in diameter, over 3 football fields. Scientists can link the signals from an array of separate radio antennas to focus on tiny slices of distant space. Such arrays act as a single immense collector. This giant New Mexico array uses 27 parabolic dish antennas shaped into a giant Y, with each arm capable of stretching for 13 miles. Scientists have even spread these linked antennas across the globe. One of the largest stretches from Hawaii to the Virgin Islands and acts like such a powerful telephoto lens that a baseball sitting on the moon would fill its entire field of view. Many of the greatest astronomical discoveries have been made using radio waves. Pulsars, the existence of giant clouds of superheated plasma, which are among the largest objects in the universe, and even quasars, such as this one over 10 billion light-years away, were all discovered using radio waves. Radio waves also provide more local information. Astronomical objects that have a magnetic field usually produce radio waves, such as our Sun. Thus, NASA's STEREO satellite is able to monitor bursts of radio waves from the Sun's corona. Wave sensors on the WIND spacecraft record the radio waves emitted by a planet's ionosphere, such as the bursts from Jupiter, whose wavelength measures about 15 meters. Radio waves fill the space around us to bring entertainment, communications, and key scientific information. We can't hear these radio waves. When you tune your radio to your favorite station, the radio receives these electromagnetic radio waves and then vibrates a speaker to create the sound waves we hear. We may not be able to tap our toes to the cosmic radio transmissions, but we certainly discovered much about our universe's grand cosmic dance by listening to them.
It was a dark and stormy night on Saturn. I'm Jane Platt, and this is a podcast from JPL, NASA's Jet Propulsion Laboratory in Pasadena, California. Those strange sounds were captured by the Cassini spacecraft when it witnessed a lightning storm on Saturn on January 23rd and 24th.
This is Duke University. produced by Duke University, online at duke.edu.
In this video, we're going to look at what amplitude modulation is and discover how a diode detector works and extracts the audio from an amplitude modulated signal. Within the circuits of many domestic broadcast radios, there's a simple diode detector. Although better circuits are often used now, the diode detector found favour because it was cheap and very effective. Before looking at the diode detector itself, let's first take a look at what amplitude modulation, or AM, actually is, and how it carries information like audio. The basis of any AM signal is called the carrier. This is the radio frequency signal without any modulation applied whatsoever. Next, we need to obtain the audio signal. This is used to control the amplitude of the overall signal. This can be done using some form of mixer in the transmitter. It can be seen that the result is that the level of the radio frequency carrier is changed or modulated by the audio. At the receiver end, the next issue is to recover the audio from the overall signal. How do we do this? It's often done using a simple diode detector. With an ideal diode characteristic, no current flows in the reverse direction, and there's no resistance in the forward direction. In reality, the actual characteristic is more like this. A very small amount of current flows in the reverse direction, and in the forward direction, it takes a certain voltage for the diode to turn on properly. This turn-on, or knee voltage, is between 0.2 and 0.3 volts for germanium, about 0.5 or 0.6 volts for a silicon diode, and around 0.2 to 0.3 volts for a Schottky diode. When an alternating signal, like a radio signal, is applied to a diode, only half the waveform passes through. Half is removed because current can only flow in one direction. To see how this works for amplitude modulation, we look at the RF signal. And to help, we've illustrated it by including a red line to show what is called the envelope. The signal is passed through the diode, and this removes one half of it. This is then filtered or smoothed to remove the radio frequency components, and this audio can then be passed into an audio amplifier. An example of a simple diode detector is seen here. The signal from the previous stages of the radio is applied to the diode. A capacitor is present to remove the unwanted RF elements, and then this is applied directly to the volume control and the audio stages. Like all circuits, the diode detector has advantages and disadvantages. On the positive side, it's very simple and can easily be built using a single diode, and its simplicity also means that it's very low cost. But it also has some disadvantages. It's not very linear because of the characteristic of the diode, and this introduces distortion. The detector is not particularly sensitive and needs relatively large signals to operate as a result of the diode turn-on voltage. It's also prone to the effects of selective fading. This is the distortion that's often heard on short-wave bands as signals fade in and out. In summary, the diode detector is very useful, but it has its limitations. Its simplicity has meant that it has been in use for very many years and will remain in use for many years to come.